Okay, what's my computer's problem? Why my computer, there's some echo back. I didn't, maybe here, okay. Now, okay, now it's okay. I mute my laptop computer. Okay, it seems like we still have a good number of people left after model part. Hopefully online people can hear me okay. So my name is Jake Liu. I'm the deputy head of prediction and assimilation and risk communication section at our lab, NCAR lab. So Bill and Mike do that. They are in the modeling side of two sections. We work very closely. So before I dive into the some detail for the MPAS-JEDI, I just want to acknowledge my MPAS-JEDI team. So here a listed name, I will not call their name one by one, but this is NCAR MCube's team. The JEDI itself, there are larger teams, there are various groups from NOAA, NASA, UK Met Office. So that's the NCAR team. And currently we have several staff. It's not all full time, but there are other people formerly also contributed. This project we started about 5 years ago, early 2018. So now is more than 5 years. So we made our first release in September 2021. And this development is largely funded by US Air Force. I'm currently the PI and Chris Snyder is co-PI. And also we jointly collaborating in the, with JCSDA. So what I will cover today with this with more than 1 hour time. So I will give you some brief, little more introduction about JEDI and MPAS-JEDI. Just give you the background. Afterwards, when I talk about the setting, you will understand a little better why the setting that way. And how to obtain, build, test the code. Okay, we just cut off early this week a 2.0 code. And then I will give you some real world application demos. I will also, like Michael, I will log on to the Cyan computer, give you some idea how to run some different things, different settings, including 3D VAR, 3D EMR, and the dual resolution capability, and how to do the hybrid, also the regional setting. So I mentioned we can do also like model, we can do both global and regional. And in the software, we also developed diagnostic, some graphic package you can also use. And I will not have time to do some demo, but I will also introduce you some other package NCAR team developed for the data simulation workflow and the observation conversion. So let me give you a little bit introduction. So JEDI is a named Joint Effort for Data Simulation Integration. That's a project led by Joint Center for Satellite Data Simulation. So really, this effort, assembly multiple groups. There are NASA, NOAA. They are working both with FA3 core, and there are Ocean, CIs, and NCAR working with MPAS core. UK Met Office working with Airfreak, this Navy using Neptune. So all these different models can connect to those kind of model, so-called model agnostic components. So these components are mainly including 4 components I mentioned earlier this week. So OOPS is kind of a abstract layer, mostly writing in C++. Including multiple minimization algorithms, and also even including minimization is more for variational data simulation, but also include LETKF solver. And there are a lot of definition of abstract of this cost function. Basically, data simulation, we minimize this cost function. And the UFO, the Sabre is basically handling the B matrix. The B matrix we call the background error covariance matrix. Okay, and the UFO is is so-called unified forward operator. So basically, it's the observation operator. It's not just the forward operator, also including the tangent linear and the adjoint. Sometimes it's Jacobi operator. So this in the equation, this H operator, also including the linearized version of the operator. So this part also including R matrix. R matrix is the observation error covariance matrix. It could be diagonal or could be also supporting the correlated observation error. Another day, Joseph asked, even though we didn't try, but they're supporting that capability. So Yoda is handling the Y. The Y is observation operator. So including the so-called Yoda format, basically including two formats. One is HDF5, another is ODB, ODC used by ECM, WRF, and UK Met Office. So basically, this format and the UFO also connected to the two important radiative transfer model. RD12 mostly used by European countries or other countries. CRTM is in US. This for radiance data simulation. Okay, and all groups, the different groups focus on their own model hooking up to this common framework. But all groups contributing to the whole ecosystem of the software package. So that's kind of a little bit background. So how we do this data simulation? So basically, the main thing is we call hybrid 3D 4D EMR. Okay, we can also do 4D, but not for MPAS-JEDI yet. Because we don't have the tangent linear adjoint ready yet for MPAS model. So basically, we don't exactly minimize this non-linear cost function. Basically, we minimize this linear version of cost function. We call the incremental formulation. Okay, so why we call the hybrid? The hybrid is really in the B matrix. The B matrix is a weighted sum of static B and ensemble B. Okay, static B is BS, then there is the weighting factor. Okay, and ensemble B, we also need a localization. So localization is indicated by L. So this is element by element product. This is also a basically localization matrix is a correlation matrix. Okay, to reduce the ensemble noise. Okay. And error matrix also we do is using so-called bump. The bump is inside the Sabre. So basically the bump is handling the spatial correlation. Okay, in vertical and horizontal and vertical. Okay, I will not have time to explain the detail about this. In my paper, in our paper, we gave a lot of details about this mathematical formulation, how it implemented. And the analysis variable, as I mentioned, so basically the temperature, UV, Q, specific humidity, surface pressure, and the hydrometers. And this B matrix, static B matrix, including the multivariate correlation. That's, we use psi chi and also unbalanced balance variable. That's the kind of elements in this software package. Documentation wise, JCSD have a kind of comprehensive documentation, but in my view, is not fully for from user perspective. Maybe it's more useful sometimes for developer. So you can check the JEDI documentation that pump up the some web page. So inside this documentation, NCAR team we wrote a portion, the chapter for MPAS-JEDI. But that's expect about this September last release 1. So the information is not up to date, but I think still useful. So we plan to add more documentation over the maybe next year or so. So stay tuned. But this today is kind of a beginning. We start to provide some community support. Today mini tutorial I mentioned September. We plan to give you some in-person tutorial September. So let me okay. I should give you some time for this point. Is any questions in terms introduction, formulation before I jump into some technical stuff? If online or hopefully I'm not too fast. Okay, if not, then let me go ahead. So let me first so where to start to use this software. Okay, this is all public. So JCSDA MPAS bundle tree release. So let me just open this. So you can see here. So basically, if you click here, the default branch will be master, but master is not really up to date. So there are developer branch. So developer branch is kind of aligned with our internal one, but I suggest you this one will be more stable. So at least I hope over next year also this kind of stable branch. Our team can provide some support. So we don't want, multiple versions. So just to check this repository, GitHub repository there are two key parts. So one is this file. Okay, there README file. You can just simply follow the README. You should be able to compile. But before that, there is a tricky part. Because that's building environment. So that's kind of a little bit different from the WRF or MPAS. So WRF MPAS mostly you just need NetCDF or PNetCDF or PIO. But this one there is more library you need to install, and they are changing. So I listed the web page. So NCAR team not currently responsible for this. So there's so-called Spark Stack. So currently we are using this package 1.3. So if you do, you need maybe download. This is all open source software. Okay, you can. I will demo you what modules load, what library there. So I will not go too much detail. So the JCSD folks are supporting this. If you have questions, so you can. So I will demo you on Cyan. So Cyan everything building environment installed. Okay. But I don't think, I didn't try it myself, but I don't think it's too hard if you just install this yourself. They should have documentation there. So after that, you can just follow this step by step, just maybe 3-4 commands. You will build everything to some time. I will give you some demo. But here, okay, you can look at. So the mechanism for build from this JEDI software is CMake build mechanism. That's not like WRF and MPAS. Okay, so CMake is kind of more modern. And they also use a software package called EC build. It's kind of automatically collecting everything. So in the CMake list file, so basically list bunch of repositories. So that's one thing a bit different from WRF MPAS. Just one WRF MPAS, basically just one single repository. Here is multiple repository. So you can, in principle, you can download or git clone each one by one manually, but that's not the way we recommend. So I will show you how to do it. So basically, you can see the repositories, the OOP, Saber, Yoda, UFO I mentioned for. But there is one, the CRTM. The CRTM is you also need that for the reading state simulation. You can also use RD12, but RD12 is turned on in the public version because that's the license requirement. You have no access for now. That's under JCSD internal. And then you can see there are two repositories. So one is for the model. Okay, this is the internal MPAS model. So that's the one we are using now in MPAS-JEDI. It's not official 8.0 yet. But even though here this is internal, but it's public repo. Okay, so everyone can access. And so I cut off a branch like JEDI 2.0, and then there MPAS-JEDI repo. This repo is kind of interface, kind of to different common component. Okay, there's some testing part also. Okay, then there was another part. So basically the environment setup. So this one basically on Cyan, we load the different modules. Okay, that's already installed by ZCSD folks, so we can do that. So now let me jump to the jump to just give you some. Let me log on to the Cyan. Okay. Yeah, hopefully after this, you are also convinced MPAS-JEDI is also easy to use. I think is the case. Let me jump. I prepare a folder. Let me make it larger, then everyone can see a clear. Let me. Okay. So let me just okay. I think hopefully everyone can see clearly. So let me just create a folder. Okay, folder. I make the MPAS. I just use MPAS bundle, 2, for example, 2.0. Then I do MPAS bundle 2.0. I will do a little bit slowly. Then you can. So first we get clone. Clone, you can clone a full repo, but you can also clone a branch. Branch is the release. Now is the release 2.0. Then you can just copy. I normally do the copy. So GitHub. So here. So if you just clone like this, the folder will MPAS bundle, but I normally, my personal preference, I just use code because upper level already named the MPAS bundle. So now here the code is the MPAS bundle repository. So in this repository, there is no actual code. Okay, it's just some files to tell you where to find the code. So now the on Cyan, all you have already have your build. So we just source the loading this one basically load the Spark Stack building environment. Okay, you see there are 90. There are 90 kind of scary. I don't think you really need 90 libraries for building MPAS bundle, but their folks just install everything for us. We are happy, so that's no problem. So you can see in this 90 pack, there are a lot of Python related. There are a few is kind of like the ECK, the FCK. There's some software from WRF. That's kind of outside the software you use. They're easy build. They even build pre-build CRTM for you. Okay. So that's the compiler also here. And one thing I should mention that as you can see, I loaded the GNU version, version. Also, there are 4 files you can use C#, but there are also Intel version of this But the entire version, I should give you a warning that we didn't extensively test executable build by Intel compiler. It builds, but we feel there's maybe some memory leaks, something like that is not running stably or something. So that's I recommend for now you stay with good GNU version of when you do the compilation. Okay. So after you have all the building environment, now you want to compare your code. So basically, my personal preference, I just make it directory like build. Okay, then I go to the build. Then now your building environment have a software package of EC build. Okay, the EC build is a ECM WRF software is kind of basically is the macron of CMake. Okay, this CMake mechanism. Okay, then you do the code. So the EC build input is basically that CMake list file to automatically finding the different repositories and declone those repositories automatically for you. Okay, so not download the different repository one by manually. Okay, so this will take maybe 1 or 2 minutes. So I just let it fly. But okay, so that's the. So after this EC build, EC build is CMake. There's something they will automatically generate. The CMake mechanism automatically generate make files for different repositories. Then you can just make. Okay, yeah, just let it go. I will not build will take a bit, maybe 20 or 25 minutes. I have already pre-built code, so you don't need to wait a half hour for build, but just want to go this part, each build part. Where we are waiting, is there a question for now?
Hey, Jake.
Yeah.
This is very nice. I like the fact that I don't have to like go figure out what to download. So two questions. One is that these build environment setups, like do you guys offer support for like trying this out on a different cluster, say on the Ohio State supercomputing cluster? Okay, you do.
No, we are not supporting that. Okay,
I mean,
yeah, I don't think that's it. We could, but basically, you better you ask JCSD folks for building environment Spark stack.
Okay.
Yeah.
Got it. And a question I have is, how big is the Spark stack going? How much space is that going to take?
Like, that shouldn't be too. This just libraries and. I have some build library on SIM. I can try, but that should not big deal.
Okay, so it's probably at most a few gigabytes at most.
Yeah, I guess so.
Okay.
Yeah.
Okay.
Yeah.
Okay, got it. Thanks.
Yeah. Yeah. Someday, our team, someone tried before. It shouldn't too hard. I know the one lady and they very savvy for those things. They can build themselves, no problem. So it's yeah, but sometimes I know this can be tricky. Yeah, so that's the yeah, I will I think I can stop here.
Sorry, Jay, can I ask a question over here?
Oh yeah, me.
You mentioned that the MPAS version is not at version 8 yet, and I recall from past talks also that there are some changes that are needed for MPAS-JEDI to be fed back into maybe the MPAS version 8.xx version. So do you have a rough timeline of when those changes will be merged?
I think the Bill can answer better.
Yeah, we expect to release that somewhere in early October. So soon. And we will announce when it's released.
Yeah, so one nice feature we have is Bill yesterday mentioned so-called two-stream IO. So that's can save, we run a lot of cycling experiments that reduce your disk space. So that's quite nice. So I will show you a little bit how we work with 2-3 mile. So yeah, they take a little time because it's, the downloading, and it's not just downloading the code. There are some test files, the binary files, like CRTM. So what's the time? Okay, now it's 10. I still have some time. Yeah. So let me jump to the. You see my. Yeah, I have another question. Yeah.
Yes, while we're waiting, I'm out of curiosity, are there any plans to directly pipe MPAS into JEDI? That means without having to write an output file from MPAS, because that would save like this space really immensely, especially if we're trying to do any kind of ensemble stuff. Yeah.
What do you mean by complete?
That means that MPAS doesn't have to create an output file that into the disk and JEDI reads the disk. That goes straight from MPAS into JEDI. Is there any plans for that, or is it just?
Not in short term, I don't think so. That's need an infrastructure, change, like CSM kind of thing. Yeah, that's is 4D thing. Yeah, 4D we also have different way you can do, forecast online, in flight and directly do, but normally as currently mostly still you need a output on disk, then you read. Yeah.
Got it. Thanks.
So now I finished. There is something in chart. First, okay. So now you see, okay, the build folder is empty in the beginning. Now you see something here. Okay. So basically you have a lot of the make files is automatically generated. Okay, from that CMake list file. Then you just make, I usually use 8 processors to speed up the build. So it's kind of nice. They tell you the it take some time. The percentage of progressing, so so, okay, how quick or how slow they build. So basically this GNU compiler, I use 8, I think take maybe about 20 minutes. So I will not go to end. So but this basically kind of the download the code and build. After build, okay, I have pre-built code already. In another folder, okay, that's the MPAS bundle. The release public. That's exactly the procedure I showed you, how I download, so now I have built a directory. Okay. So now first, let me check what's the executable generated by the build. Okay, the bin directory. There are a lot of there. Okay, it's not just single executable. Okay, there are how many? Let me check. So that's okay, there are 169 executable. Okay, that's kind of a lot. But there are a few is for the MPAS. We even build MPAS model. We have named a little slightly different name, MPAS atmosphere. That's for the forecast. And there are also even init, MPAS init atmosphere. So other is MPAS related is MPAS-JEDI related executable. So most important one is the MPAS-JEDI variational. So this one is doing the variational data simulation. There are also ENKF is doing LETKF. Also there EDA, I mentioned EDA basically running multiple of EMRs. There are some others, you don't do data simulation, but you can simply do the HOFX. Okay, it's kind of, you can calculate model equivalence to the observations. And there are a lot of code is from other repositories, OOPS, YODA, UFO, and in the OOPS code, there are some toy models. like a Lorentz 95 model. Okay, so there's something, so a lot of there. So just to give you a little bit of sense. So it's kind of a different philosophy or design thing for. So and next step after you build, okay, all of. So that's she make their next step normally is she test. Okay, she test is part of she make software. So you can just do she test on the top level on the build. But don't do it right away, but you do the dash n. The dash n will tell you how many she test case in the lab. So there are more than 1,500 case you can test on top, because this test including all repositories. So you don't want to do this. This maybe take your hour, but you can do the you can go into a deeper level under MPAS-JEDI. This is all in my README file. In JEDI, if you do C test dash n, okay, we have 47 cases. So then you can just do C test. So it will run one by one. So basically, the C test, including so-called unit test. Another thing is the so-called application test. Okay, so basically, the unit test are small functions. Application test, like you are doing data assimilation, you are doing HOFX. So so that's this 47 C test maybe take maybe 3-5 minutes. I'm not sure, but yeah. So that's the T test give you a way. When you do the continuously development. So those tests, still when they said pass, it means okay, your software is functioning properly. Okay, in different words, it's like so we call the in software engineering world regression test, but the C test is not automatically okay. Those tests is you need doing something in your code. Okay, is there's some testing part of code. I'm not expert on the creating C test cases, but so basically this 47 C test case is very useful because there are, I will not go through. So I already tested all 47 is passed on Cyan, so no problem, 100% passed. But let me check a little bit what the C test include, because this is something learning material you can use. The C test, then you can go into test input. So this test input all linked to, there are a lot of YAML files. All these YAML files link to the code directory MPAS-JEDI test input. So YAML file. So that's another difference. The JEDI software package uses the configuration. The configuration using the YAML files, not name list. Okay, so that's kind of sometimes for the people not familiar with this, a bit tricky. But for example, let me just open one file like 3D var, for example, 3D var, this one. Let's give you the sense of what looks like YAML files. So what's this testing doing? So this testing is doing is that, okay, we run something and we produce with new code, we produce some result. But the previous version, we already created some so-called reference file. The reference file is kind of like a standard, okay, not standard, but something earlier version created. Let me go to another. So this, the key message is that okay, YAML file is like a name list, okay? But there are another folder is called test output. So this folder, there are some reference files. This linked file, okay? The linked file also from the code, source code. For example, .ref. So this is all text file, okay? So then when you run this test, you create you generate this basic log file, like Michael demoed this MPAS log file, but this is JEDI log file. The log file, the portion of it is using some grep or something, create some run.ref file. So basically what this C-test is doing is compare this the existing reference file to the generated file by your current code. If they are identical or they are different but within a tolerance, you test passed. Okay, so that's why what's the meaning pass. Okay. So that's if you diff these two, for example, these two you will say they could be different, but here, yeah, so they basically are identical. Okay, because that's latest code. So that's provide a way, a kind of robust way, check your software continuously every time you make commit. And this procedure, the C-test procedure is automatically on JEDI's repository using CI/CD. They run each commit, will trigger a automatic C-test procedure on Amazon Cloud. Okay. Yeah, so that's very nice. The infrastructure are built by the SDA. So now let me just go into test input. So open the 3D var folder. So we will leave the sense what looks like this configuration. So you'll see there are some name list file that's for the model setting because the MPAS-JEDI build the model inside. Okay. And also parallelization, partitioning also use the JEDI, also use the MPAS model. So there are stream file doing the IO. We also make use those things. And that's here we define the analysis variable, temperature, specific humidity, and the file hydrometers. And this is the analysis variable, but there are also background. So background, there are more variable listed here because the background is the analysis is something you will change those variables. But when you do the assimilation, for example, some surface variables, you don't modify them, but you still need those input for calculating, for example, radiance state, right? So that's you have more variable like snow vegetation, some soil moisture kind of thing. And their background, here using restart, but basically we don't use restart file. We call the MPAS-out. If you know the WRF, the WRF out and WRF restart. So WRF out is kind of superset of a restart file. So we also use, and there are other background arrow setting, their observation part. So I will show you later. There's some real world case, and this C-test case for them run quickly. This very tall case is just 6 levels. 480 kilometer resolution because you can run in one single. So this for the quick code test. Okay, but those settings is kind of useful. You can still learn something from. I will have no time to explain all 47. This what to do, what they are for, but you can learn something. And in September, we will give a bit more instruction about those settings. So, okay, I think I finished the first part for the obtain the code and the build and the C-test. Is there questions at this point? Yeah, Joshua, I like you. Yeah, Kevin, yeah, you are next.
Sorry.
Yeah.
I have a silly question about about the analysis variable selection in the YAML file. So I mean, I understand for var methods, the selections are limited by what we have in the control variable option in the control variables of your B matrix. But for the LETKF, you could in principle do any variable with it, right? So I was just curious, is this system okay if we ask it to update a a variable that's not in your B matrix, but with the LETKF?
Yeah, very good question. I didn't try it myself. I already care too much. Evite tried. She may be able to help later, help answer. But my guess maybe not. It's not that design that smart. You just add a variable, then code or automatically handle it. I guess you maybe still need some coding work. I guess. Evite, is that right? Yeah. Okay.
Let's test it.
Simon, you have question? You probably.
With the MPAS model and MPAS in it, different are they from the past release?
Oh yeah, we have version difference. That's based on maybe 7.3, and above that we have modifications. One major thing is the so-called 2.3 mile. So that part. And also I should mention that I recommend you to build MPAS for MPAS-JEDI for now using GNU compiler, GNU compiler, but I recommend you build a model separately using Intel if you want to speed up. I think Intel is quicker than faster than GNU compiler. Yeah, there's one thing I forget to mention. In the CMake file, the by default here. This last piece for this part. CMake file. So we have a switch for the MPAS model build here. So the MPAS can build in double precision or single precision. So by default, when you download the code, is the double precision is on. If you change this to off, so that will be single precision. Okay. And we also recommend you to do the single precision when you build MPAS-JEDI, because okay, when you turn on this model build for single precision, MPAS-JEDI is sort of like a partially single precision, okay, because there are a lot of repos. That could save you a little running time and memory. But when you run this with, when you compare this with single precision, the C-test case will be failed. Some case will be failed because those reference files created by double precision build. Okay, so that's just a little trick here. Yeah, I think that's the, and also mention that even though the MPAS model in this MPAS bundle, MPAS model, including CMake type of build mechanism, you can still build our version by separately using traditional make mechanism. Okay, because this two probably set. But I hope in the future when we merge together, I guess Michael will have to have the CMake build mechanism in your official release. Yeah. So at this point, I should move on. Okay. So now is the it's kind of basically you download, build, you see test, basically the code test. So now let's go to some real world application. Let me go to first 3D VAR. Okay, 3D VAR it sounds easier, but it's not always. So one thing, one thing I should, 3D VAR, there's some 3D VAR, if you know data simulation. So 3D VAR, you need a static background error covariance. So you need to do some statistic. Okay, we do provide, let me go to the website first, MPAS-JEDI folder. So here you go to the 2.0. There I will mention later there in this repo we also our former colleague JJ Bright he developed a lot of diagnostic graphic package. I will just show you one example later time. Let me see the timing. but there are another folder is kind of under test, I believe. Yeah. So there is covariance. So this part is we don't have the documentation yet. Hopefully we will provide something in September tutorial, but this package also included in this repo, fully open source, but you can do the background error covariance statistic based using NMC method. Okay, globally, we mostly try globally. We didn't try too much yet regional, but should work. Okay, so now let me go to the real world application. So now is this 120 kilometer case, this 3D VAR. So 3D VAR, I already linked all input files necessary in this folder. So you can see, so basically, you can say first of all, there are a lot of files is from model side. Okay, this ozone, RTMG, and also stream. The stream file. The stream file is a little bit different than the. So we made some modification. I don't have time to explain very detail, but you can see the stream file. This one, the stream atmosphere 120 kilometer, is like your model runs one, but this one pointing to other two stream list. This stream list file is basically the analysis variable list. For example, if you open this file, you will see some analysis variables there. Okay. Yeah, this is not all analysis variable, but there's something. So here is just a few variable listed here. So this a few files of analysis, background, and control like control variable. In the traditional sense, there velocity, potential, stream function is here. So basically, because we make use of MPAS model mechanism for I/O and for partitioning or parallelization, and we also need this parallelization, the partitioning files. Okay, so you see this, you need it. Okay, and the name list also, you need a name list. But the name list, there is one parameter I don't think a model folks they need, but you need to turn on this. I think in the very end. So a simulation config ZDI DA equal true. So you need to set this be true, to run the simulation. There are some other tricks, this related to the two-stream I/O. So basically, traditionally you do the restart file, but now you can do configure data simulation section equal true. I will not give you detail here, but the current way design the two-stream is not very clean. Michael is working on to make it cleaner for general use. But basically, this name list file is like your file for doing the model forecast. Okay. But there's a couple of key parameter related to data simulation. And other files really is what you need is just a background file. Okay, background. So this background file is linked to something, but basically this background file is not restart file. Is I call it normally is MPAS-out file. That's including K parameters, but exclude those static field. The static field every time is same, right? You don't have to include it to save you some disk space. And the analysis file, there are one trick is that it's better, or I think you have to copy before you run the analysis. You need a copy background file to analysis file. The reason for that is that the MPAS-JEDI don't write out all variables. We only write out the modified variables. So you need something already there. Then this write file just file variables for UVTPQ. Other they could be save you some IO time. Replace the existing netcr file. That's kind of a little bit trick. And observation input is is in the dbin folder. Okay, it's here. There is this H file. File is HDF file, basically HDF file. So each observation type is separately. Okay, I can go into, basically, this HDF file, their grouping. I can go into, if you NC dump, you will see what it looks like, for example, the reading state. Oh, that's, so you'll see some grouping, these groups, this HDF5, the reading state, basically that's brightness temperature, their observed value, OBS value group, their bright temperature, and there's some observation error. So that's how many observations you will know. This observation you have, 15 channels, there are 9,000 locations pictures. Okay, so that's there are some metadata, lat long information all included in this file. So that's the input file observation. So after DA, you will see some observation feedback under this folder, db out. So I will delete these files for now, then we can run it. And yeah, let me open another file, is the YAMA file, that this the real world configuration. So in the beginning, there was some, I'm not expert on YAMA setting, but basically, there are a lot of examples you can just start from, then you make some modification. And the YAMA basically is the K value mechanism. There's some K here, there's kind of like variable. And what's the value for this variable? And they are also supporting the nesting, they call this nodes. This is nodes. So there are a lot, it's kind of in the first glance, you will feel a bit complicated. In this file, how many lines? Let me check. There are 494 lines. Okay, this seems not like a traditional name list. You probably have just tens of lines, but this sometimes could up to a few thousand lines. Okay, but you can gluing them together from separate files. So there's CRTM setting this for the reading state simulation. And there are some, let me start from, this zerometry. Okay, zerometry, we need also know the zerometry, zerometry is also come from the, this name list string file. And the output analysis, where you put analysis, so you can rearrange as your personal preference, where you do the input, where you do the output, all in the some YAMA setting. And the minimization, you have multiple choice for minimization algorithm. So we use the so-called DRPCG algorithm. And how many iterations you do the 50 iterations. Okay, you all can control in this. And the next section is the cost function section. As I mentioned, there are analysis variable. So now I remove the hydrometers, just to include dynamic thermodynamic variables. You have state variable for background. You load in more information in the background where you can find background. So here is the setting for this kind of important part is the background error covariance setting. Follow my the formulation. So their part for static setting, for the ensemble part, what's the factor? So I have other setting for hybrid, but for the 3D bar, you all may need here is the background arrow, and you use this model, the so-called bump package. So what's the here you see the stream function velocity potential. That's to control how you do the multivariate correlation. Okay, I have no time to explain more detail, but there are pre-generated using that statistic package. pre-generated the static background error covariance files, okay, in some location. And there also tell where is these files and what's the file names. Okay, I will not go to the folder to show you, but just telling you the idea. And was, you know, there not just one single file, there are multiple files for multiple purpose. For this one is really for the cross correlation, multivariate correlation. Another part is for the standard deviation in each location, model location. Okay, so that's another set of file. And another, there's 3 parts of setting. Another part is for the so-called vertical balance. The vertical balance is really, in my sense, is really to tell you the multivariate correlation between mass field and you know, and the dynamic field. So that's the background error part of setting. This only for static part, because it's 3D var. 3D var, the 100% weight in the static background. Then the bigger part is why there's so many lines is because it's setting for observations. Each observation type have the you know, could be tens of lines or even hundreds of lines for each observation type. Okay, tell you where you take the observation input, and also tell you where you write out observation output. So after data simulation, we will output so-called data simulation feedback files. So this OBS out DA aircraft. And you know what observation variable you want to assimilate, temperature and wind field and specific humidity. Okay, you can remove one, then you can. So this is good thing. You know, looks complicated, but the complication give you more flexibility. So you can turn off, turn on something easily. You don't need to modify the code. So previous traditional software, both WRF-DA, GSI, you don't have such kind of flexibility. Most of the time, if you do this, if you want to turn off, you don't want to assimilate specific humidity, you have to modify the code. Now you don't have to, you just doing the YAMA setting. So that's something nice. Okay, there are a lot of flexibility. I will not elaborate a lot. For this test case, I have you know, 5 types of non-radiant state, radio-zoned aircraft, GNSSRO, and also include 6 MSOA. So this 100 of lines I will not go through. So that's the kind of setting. So that's the, I think the YAMA setting is the most complicated part for the JEDI software. Otherwise, mostly when you know the model, you know the stream file, you know the name list. But of course, the another part is for the doing the background error covariance statistic. Okay, I will not able to cover that part at all for the statistic, but come to the September tutorial. So after everything, you have your input, everything, you just run the AC cell, you just Q sharp, 3D var, E cell, okay. So you have a PBS job scheduler, you just solve, first of all, before you run the executable, you solve the environment, build the environment to make sure, you know, you run the code with the environment you're building, you build the code. Then you link your executable. The executable is the, you know, MPAS-JEDI variational.x. Then you run MPI, okay. Then you have the 3D var.yama as input. It's like nameless input. Then you have da.log file is the log file. Okay, you can name for any name what you like. Then you simply just Q sub 3D var. Okay, I use 4 nodes, each node using 32 cores. So totally we have 120. This will take maybe the 120 kilometers very fast, maybe 2 minutes or 1 minute. So yeah, previously I deleted my log file, but this should. So that's the how kind of it works. Later time we'll have some output. Any question? Oh yes, today is not very good queuing. Yesterday is good. Is any question at this point? I think already 11:30. Yeah, just yeah, I cannot go with 400 lines of YAML file.
So
Yes, yeah.
I have a question about to using the observations from using an H5 format. So is there any preprocessed tool or package to convert? For example, if I have a pre-buffer data or buffer
Yes.
data to convert that?
Yes. So I will mention that in the last part of my instruction. Oh yeah, you're running.
Yeah, it's running. Quick question. Is there a mechanism to generate perturbations? Like, so in WRF-DA, I believe there's something that generated ensemble perturbations based on the CB3. Is there a
Yeah.
similar mechanism here?
I think there's some mechanism exists there. We didn't practice that much. I'm not sure. I'm not 100% sure. We have it, but we do. You know, there is a unit test called direct test. Direct test, but basically that for the, I think the static B ensemble something, so that could relate to that. I'm not sure.
Got it. And H of X executable, like what's the format of the files that it outputs, and is it, and how do we control, is it also just controlled by YAML files?
The file format output of this file is still a HDF file.
Okay, so basically, okay, if I run it on, okay, got it.
Yeah.
And it's controlled by and like this, the precise settings of the observation operator is also controlled by the YAML files.
Yes.
Okay, got it. Thanks.
And it just, you know, output data simulation feedback file, it just include more information, right? You know that. Let me say, okay, run 1 minute. Yeah, now you see some, you know, a lot of log file. The log file for the just check the root and da.log is not doing, you know, something wrong. You can check other, but here you, so it's doing the minimization. Okay, so the 50 iterations I said, you can set them all. If you don't feel it converts, you can check this. So the, you know, as the model same, okay, it's very good. Every time, first of all, when you started something, check log file. The log file provides you a lot of useful information. It's, you know, in minimization is not like model integration, but it's sort of like, right? So, and you can do multiple out loops. For this case, I only set one out loop. So one out loop. So after minimization, and we'll write out the observation output files. Okay, OBS out, DA, you know, set wind also still separate for different observation types. Yeah, it should be very yeah, a couple minutes, that should be okay, good. So yeah, it's done. So in the very end of this log file, you'll see the, you know, running time. Okay, they're 175.95 seconds. A bit of 3 minutes, right? The memory, also the memory total. The memory total and also the, you know, per task. Now we have 128 tasks. So each task is memory cost different. Okay, that tells you which the minimum memory use and the maximum memory use, the range. Okay, the totally the cost is one. So something when you memory, sometimes if you smaller number of nodes, it doesn't work. So this tells you maybe you are overused your nodes or you used not enough. So that's kind of useful information. So even tells you the memory cost. I don't think memory cost, but the you know, each the timing information about, this different C++ class. Okay, I'm not sure the memory, but there's some timing information about. So when you're debugging, those timing information for different subroutine or module also give you useful information, where is the bottleneck. So okay, it is finished. Then let's check bit. Okay, this now, so now this analysis file should be replaced, but not replaced. It's kind of, it's kind of replaced, but just some variable is modified by this software. And then you'll see the db out file, a db out folder. So db out. Okay, let me go inside. So as I mentioned, I have 5 types of conventional, no radiance. Okay, not conventional, all conventional. There are 4 MSOA. So if you NC dump, you will see, they have more information. For example, HOFX0. So HOFX0 is the model equivalence to observation at the beginning of minimization or before minimization. There are HOFX1. So that's the model equivalence to observation after minimization. Okay. If you have another outloop, you will see HOFX2. Okay, that's the second outloop after second. They're all minus analysis, observation minus analysis, observation minus background. So basically, there's some duplication. I don't think they really need all of this variable. There's some duplication. You can calculate them yourself. But so that's how. So after so those diagnostic information is very useful. That's common practice for all data dissemination folks. And also there is effective QC. So what observation is used by data dissemination? What is rejected by quality control? Also, you can see from this file. Okay, we call the data dissemination feedback file. Okay, now, so the best practice, when you're starting something from beginning, so do some graphics. Okay, there are 2 things. First thing I would recommend you check the graphic pack is also included in the already generated all of them. Let me delete them for. Then just check. There is a package we provided. Okay, there's one code. I believe that's Junmei Ban in our team coded maybe a little bit old, but it's still working. So basically, you just okay, you can input the file name. This is the two folder, upper folder. Then you just plot da.log file. So basically, this one plotting the cost function and gradient norm reduction. Okay, yeah, I'm not sure. I need a first load. Okay, load. Let me do another. Load the Python environment properly. Let me do the first source cyan. So this one I tried last night. So this to do the Python loading. So you have the Python. So now let me do the plot. /3D var here. First time, okay, already. I don't think I can go all of them, but then standalone. So I just do Python, then plot cost. So there's some warning message because that's the older version. But you can see we generate two PNG files. If you just delay, let me see the cost function. This quadratic, that's the cost function. Oh, why? Oh, yeah, why have two outloops? It looks like, yeah, something maybe DA file now. But if you have one outloop, you should have just one line, this from the beginning, the minimization, you just make a cost function smaller and smaller, right? If you have another outloop, we're starting maybe in the some here, then you reduce. So that's and you don't have too many iterations. You can also set this flexibility. If you already flat in early time, you don't have to use so many iterations. And so that's the cost function. Another one is the norm reduction, the gradient. Yeah, I don't know. I know, this room is not all people is data simulation people, but so that's norm reduction. So you should say that I should mention that cost function must be monotonically decreasing. Otherwise something wrong. But norm, the gradient norm, the gradient of cost function, the norm can be oscillated. Okay, that's okay. But you can say from beginning, that's the relative region, from the beginning, from 1 then to the maybe close to 0. The gradient, because we are doing the minimum of a function, the function, then the derivative should be 0 or close to 0. Okay. So this is good. There are another thing. There are a lot of figure Python stuff you can use, but I just show you another one. Plot die. So this one is plotting the DB out folders file. Okay. I already said, we have one out loop, so just doing one out loop, and everything should be automatic. So here is you don't have to set up this already there. So you just assign the folder, where your folder and your file name, OBS out and HDF5. Then you also run the Python load diag. Okay, we'll create a lot of horizontal distribution, also profile O-B, O-A profiles for all kind of these observation types. Okay, so that's is kind of nice. You can check, kind of like sanity check, everything works properly or not. So yeah, this should be quick. I think now, yeah, there are other questions at this time. Oh, there was someone in the room.
Two questions. First one is what types of observations can be assimilated with MPAS-JEDI? This is the same as WRF?
At this point, in general, because MPAS-JEDI make use of, JEDI as UFO, inside that UFO, there are a lot of more capability. You can assimilate a lot of satellite. But as I mentioned in my Tuesday's presentation, we experimented, maybe mostly, there's some non-radiant state, surface pressure, radio-zoned aircraft, GNSS-RO satellite track bin, and also the MSOA readings, MHS, YAZ readings, geostationary ABHI, and also ATMS. So, but we can do a lot more. But what we want to make the robust, it's not just you can turn them on, they give you good impact. So what we are trying to do is, we deliver something, it's not just a software package. We run a lot of setting ourselves, and when we deliver some configuration, that's give you some good performance. But in general, you can do a lot of more. You can assimilate a lot of more observations than WRF DA or GSI, because there's so many partners contributing to the whole package.
Second question, I'm not sure. Yeah, but anyway, they ask, could you please provide the links to the observational data used in data simulation? Where do they find?
I will tell you that later, but I can mention where, okay, already finished my figure. Yeah, that part there is convert. Currently, mostly we are trying to use, we tried, we are using is the converted data from NCAR's paper buffer for non-reading state and a buffer file for reading state. The reason doing that is that it's publicly available. Okay, well, and we provide the converter to convert those buffer data to HDF file. Okay, already I will mention that the package I already mentioned in Tuesday's my talk. But now just you have a lot of figure generated. Okay, there's called OBI, there are O minus A, O minus B, so background. So you have to, so just open one, like this mid top B observation, the distribution for writing temperature is channel 8. Okay, give you colorful horizontal map. Okay, something like this. Okay, so that's we already, it's not but there are a lot of already basic thing for doing the diagnostic. And one thing is the O minus B, O minus A statistic here, for example. The radius zone, for example, radius zone, the RMS, radius zone, the temperature. This one should be the vertical profile. Okay, there are different levels. So you see the blue curve is O minus B and the red curve is O minus A. O minus A should be smaller than O minus B. And that's the vertical level, and the right-hand side give you the observation count. Okay, so that's, and for a lot of, so that's the, I think I covered, basic, basic thing for the 3D bar setting, and you can produce some basic basic graphics. And in this graphic folder, there are a lot of other things I will not cover today, but yeah, anything jump on now? I still have 10 minutes also, but I just I will not run another thing, but just tell you the setting. So let me just jump to the hybrid setting. Okay, the hybrid and including dual resolution. So the earlier one is just a single resolution. Your minimization and your outer loop is in the same resolution, your model. All is 120 kilometer. But when you do 3D EMR, for example, you need ensemble input. So ensemble input, if you do the, for example, you 30 kilometer, you do the 3D EMR. Your ensemble also in 30 kilometer. You need to have ensemble forecast for 80 members or 60 members. That will be very costly. So what we so-called dual resolution capability, you ingest your ensemble at a lower resolution, okay, 80 members. But then you also do the minimization at 60 kilometer. Then after you get the analysis, basically that's the analysis increment. Then you add your analysis increment to the higher resolution background at 30 kilometer. Certainly, there is an interpolation process internally. You don't need to worry about outside. So I'll build inside. So just so that doing that way. I'm just give you a little bit idea how it works in terms of setting. Okay, you still have a lot of this model related file, but this time because you need a two set of resolution, so you need a partitioning file for two resolutions. Okay, and you also need a stream file. There are two name list file for different resolution. You also need a two stream this file for two resolutions, because you need to do the I/O for two different resolutions. So that's a bit trick there. Otherwise, it's just it's just a trivial. Other setting like in the here the 3D hybrid. So the hybrid, as I mentioned, observation part is completely same. Okay, in the YAMA setting. The difference in the background error covariance part, the B matrix, I listed that the equation, right? For the hybrid, then you need a combination here. For example, here, the background error now, covariance model, you need to set to hybrid. Okay, then you need to tell what's the weight between the static B part and ensemble B part. So in this case, the static P part we set 25%. Okay, then afterward their ensemble part is 75%. They need to be one when they sum together. Okay, and the same setting for the static B setting, you have pre-generated files. For the special correlation and standard deviation and also multivariate correlation. Then you set the ensemble B. Ensemble B weight equals 0.75. Okay, then your ensemble B ensemble. So ensemble, you need input ensemble members. You need to tell where your ensemble input it. Okay, now I have the ensemble. Oh yeah, there are two parts. So one is the ensemble file input. Another is the localization. So localization is in the equation is the error matrix. Okay. So localization file you also need a pre-generated. Okay, using some bump in, using some application in the test like, and then you need to tell where is the ensemble input. So in this case, I have 80 members of ensemble input. So some naming convention, where the folder, the file names. So it's just a couple line. You don't need list all members, very long, but you have some. The YAMA tells you some smart way to tell you how to compare 80 members. Okay, so that's all. Doing the hybrid versus 3D one. And if you do the not do the hybrid, if you do the just the pure EN1, you can delete the static part, right? You just keep the ensemble part. That's all. So that's I hope I convince you it's easy. Okay, it's not so complicated. So I think there's something and you have a lot of flexibility and you have a lot of functionality leveraged by a lot of groups. So that's the. So I will not run this, but basically they are same. But so that's the yeah, I think that's the citing. I think I will maybe give you a little bit of rest. You have 5 minutes, but is any question? Yes, we are.
So for the 3D EMR, is that including the recenter? I mean, is for example, if I run a long time cycle in DA, so the ensemble member and the variation will be just depart.
Yeah, very good question. No, it's not automatically do because but now is I'm talking about I didn't cover LETKF. Okay, that's purely for EN1. EN1 just give you one single analysis, a deterministic analysis. But when you're doing together, EN1 plus LETKF, you probably need something in your script workflow, or you do some I'm not sure internally they can do research. I don't think so. You need to do yourself in your workflow, I think.
Thanks, Jake. Just a quick question on the YAML file setup for the hybrid ENVAR. You mentioned if you wanted to do just straight ENVAR, you could delete the static section. But could you also just set the static weight to 0 and the ensemble weight to 1 and just keep it?
Oh yeah, whoa, that's a good question. We didn't try that. I think it may work.
Okay.
Yeah, but one trick, it's not sample like deleting because the YAMA. The one trick is that YAMA, you have to align your YAMA settings very strictly. If you miss a line, it will give you some error. So when you do the pure inverse, normally we will maybe you need to move left, maybe two column or something. Yeah.
I have a actually two future development questions. One is that, is there like a plan in the somewhat far future to turn this into a GPU code? Because I imagine VAR methods are insanely compatible with GPU systems. So any plans on that? And any sense of how many years it's going to take?
Yeah, I think people is talking about this, data simulation is perfect thing to apply to with CPU, but I don't know in any group is really seriously actively working on this, but I heard of this with some plan, but yeah, I'm not aware. Yeah.
Got it. And the second question is, how are there plans or like anything ongoing to put serial filtering techniques in? So like one observation, assimilating one observation at a time kind of technique?
Yeah, I'm not sure. I know the basically cross-town the NOAA folks working on the analytic capture. I know there are different groups is working on the different filter nonlinear one or something, maybe based on Zeta. But I'm not aware they are contributing back yet. But I guess there are some groups out there.
Got it. Thank you.
Okay, I think I don't have to go straight with Nguyen. I have one for the regional, but I think I can stop here, and I encourage you if more detail come to September's watch, and Bill will handle the official announcement maybe in sometime in July. So yeah. Okay, I think I will stop here. Give you the time, maybe you need to go to airport 2 minutes earlier. Okay, thank you very much.